The Quiver2D244 and PhasePortrait244 functions both deal with first-order autonomous physics differential equations with two components, which we can write in the form dx dt is some function f of xy, and dy dt is some function g of xy. The autonomous bit means they don't depend on t. We have these two functions f and g that are going to be involved with both these functions. The quiver will draw a slope field or a direction field for this system, and PhasePortrait draws sample trajectories to give you an idea of the phase portrait for that system. So let's look at both of these functions first. The quiver function takes in f and g like expected. These are expected to be anonymous functions of two variables, x and y, in that order. Bounds on x, bounds on y, and a color for the different arrows in this direction field. It works the same way as Quiver244 did, but just now we have two functions. We have x and y are two variables, and the color is still the same. The same it is before. It'll also draw two plots, one scaled and one unscaled. The first one will be normal, the second one will all be scaled to be length 1. For PhasePortrait, the idea is similar, but now we're going to draw trajectories instead. So we've got f and g are two input functions. Again, functions of x and y. Bounds on x, bounds on y, and then bounds on t, which are going to set up how we draw these sample trajectories. So it's always going to assume that the x0 and y0 are values at t equals 0, and you can set initial and final values for t to determine how far these curves stretch in and out. At the end, it'll always be set to the axes being x-min, x-max, y-min, y-max, so if things flow off of that, they're going to just disappear. But as long as you get the picture you want in that range, then it's going to be okay. And you can sort of set these however you want and play with them to see what you want to get. X0 and Y0 can both be vectors, but they must be the vectors of the same length. And so you're pairing up one from each to give you the different coordinates. It's not going to grid them. It'll just pair up one at a time each of the different values of X and Y to give you a phase portrait. So let's see what some of these pictures might look like. Let's define some functions here, and then we can draw some plots. Push that much there should give us a quiver plot. There we go. We can see it right there. Then we can take a new graph and draw the phase portrait. I'm just going to go with -1, 1 for the t value. We'll see what that looks like and decide from there. And let's just pick one value here, 1, 1 for our x and y, and see what that gives us. A neat curve there, but it's not much of a phase portrait. So this black dot here indicates the minimum t value. In this case, that's at t equals -1 is where that dot is, but that's going to tell us where it starts and give us an idea of the flow direction of this just from this picture alone. Now it's nice, but that's not much of a phase portrait. A phase portrait has a lot more curves on it. So let's add a lot more points to this. Let's add a whole column along x equals 1. So we'll do 1, say 5 times, 2, 3, 4, 5. And then we'll add different y values here. And those are all the same length, so we're good. I can now run this, and we're getting more of a picture here. Right, all these curves go through 1 at various heights, and they sort of follow the way around this way. Now, if I want to get a more full picture, I want to put a lot more points in here. So we could say, do the same thing, but now with -1s. And now I kind of want to see what's going on with these, so let's extend the range a little bit. Let's, instead of going from -1 to 1, let's go from -3 to 3 in terms of t values. And so you can see that there's a bunch of spiraling going on up here at the top, and there's some funneling going on down here as well. And you can sort of get an idea for what's actually going on with these different curves at this rate. You can also add a lot more curves, which I would recommend if you want to get a full picture, add more, make them more dense. One way to do that in an easy way is to use with the ones command. So in Matlab, the ones command, so if I do ones of say 1, 10, gets me a 1 by 10 vector of all ones. Which means I can write this whole like 1, 5 times as just ones, 1, 5, and the second part as -1 times ones, 1, 5. This will still work. And now you see how you can make this fill in a lot more detailed, right? If I make this say 15 and 15, I can replace these now with linspace commands. So a linear list from -3 to 1 with 15 elements in it, and do that twice. Now it's going to fill in the graph a lot more because there's going to be a lot more curves on it to draw. And so you can see how by taking different values, making more and less curves, you can get a bigger range and a more full picture of the phase portrait for the system using this function here. Again, as always, you could just write the functions directly into each of these spots, but depending on what the function is, if it's complicated, it might be simpler to just put it out front, especially if you need to use it multiple times, call it its own variable, and then put it into each one here as a different function call in itself. That's the idea of the PhasePortrait and Quiver2D functions and how they all work so that you can use these to successfully complete the appropriate Matlab assignments.